All right, new chapter. We're doing some lecture and lab so we can get some of this nomenclature stuff underway. I'm going to try to go somewhat fast because most of this should be review, and then if we've still got battery, if we've still got energy, we're going to jump a section and talk about organic compounds as well. So you may know that there's a lot of different elements. There are 91 naturally occurring elements on our periodic table. That's a lot of different combinations that you can make. Even if you're just picking two of them, like carbon and hydrogen, there are hundreds or thousands or millions of ways that you can combine carbon and hydrogen together. And each of those chemicals, each of those compounds is going to have a slightly different name. It's going to have slightly different properties. It's going to have different ratios of the elements. And we as chemists need a system that we can use to name every single one of those. So we need a very robust, very rigid system that lets us name lots and lots and lots and lots of different elements combined in one particular arrangement. So once we start getting to the nomenclature part, you'll be like, why is this so the way that it is? And it's the way that it is so that we can describe hundreds of thousands of different chemicals and talk about exactly one of them, or a small group of them at the very least, depending on how precise we want to be. When we combine elements like hydrogen and oxygen, if we look at the properties of hydrogen and oxygen by themselves, their boiling points are in the negative hundreds of degrees Celsius. They exist as gases at room temperature. If you combine them together, the properties change drastically. Now it's got a boiling point of 100 degrees Celsius. It's a liquid instead of a gas at room temperature. Hydrogen and oxygen, explosive, necessary for combustion. Water, of course, used to put out flames. So when we combine elements to form a compound, we're making an entirely new substance, and the properties are not always going to be what we might expect. I believe we've talked about mixtures and compounds. Remember that mixtures are elements just kind of lumped together. You just toss them together. They're in the same area. They're not combined to each other. Compounds, on the other hand, are when you take the elements and you actually fuse them together, you combine them together, you bond them together, and they are in a fixed, definite proportion. So like for water, we've got exactly 2 hydrogens to 1 oxygen. That's our fixed, definite proportion. It's always going to be that same proportion of 2 hydrogens to 1 oxygen. The way that we combine those is with chemical bonds. Our chemical bonds, we'll talk about these more in depth later in the class, but basically it's attractions between charged particles in the atoms. So the negatively charged electrons, the positively charged protons in the nucleus, those can interact with each other, and then they're stuck together, bonded together. We can classify our chemical bonds at this point into 2 classes. We've got ionic bonds and covalent bonds, and we'll talk about these separately. So ionic bonds are up first. Ionic bonds occur between ions. So they occur when we are mixing metals and nonmetals. So ionic, we're thinking metal forms a positive ion, and nonmetal forms a negative ion. Ionic bonds involve the transfer of electrons from one atom to the other. So when a metal interacts with a nonmetal, it can transfer 1 or more of its electrons to the nonmetal. So the metal loses electron, maybe multiple, and so it becomes positively charged. The nonmetal receives or gains those electrons, possibly multiple, and it gets a negative charge because now it's got extra electrons. And when we put these positively charged and negatively charged particles in close proximity, just like opposites of a magnet, they stick together. So the solid phase for an ionic compound is going to be a lattice, a three-dimensional framework that alternates between cations and anions. So our ionic compound is cations and anions alternating in 3 dimensions as far as the brain can imagine. Here's a little bit more of a visual way of looking at that. If we take sodium metal and chlorine gas and you mix those together, our sodium is a metal. It likes to lose electrons because it's a metal. So it's going to donate an electron to chlorine. One of these chlorine atoms is going to pick up that electron. It becomes Cl minus. So now we've got sodium plus and Cl minus, and those can sit next to each other, alternating positive, negative, just like if you threw a bunch of magnets together, they would work themselves out so that they're alternating positive, negative. Alternating because positive charges repel each other, negative charges repel each other, but if you space them every other, then it's all attractive forces all the way, or at least mostly attractive forces. And that can form a crystalline lattice, which is part of the reason that table salt forms crystals, because it's that alternating positive, negative charge. And that's why we get those crystal formations. On the other hand, we also have covalent bonds. Covalent has the prefix co, like sharing, like cooperative, together. And valent refers to a particular type of electron. We'll just say that it means electrons for now. So covalent bonds are sharing electrons bonds. These can exist between 2 or more nonmetals. So covalent is nonmetals only. No metals in my covalent bonds. Please and thank you. And again, these involve the sharing, that's the part, of electrons between 2 atoms. So when a nonmetal bonds with another nonmetal, we're not transferring electrons, we are sharing electrons. And the way that we do this is basically just putting the electrons between the 2 nuclei. They could be kind of anywhere really, but the most stable place for that electron or multiple electrons to live is between the 2 nuclei. So we sort of think of it like we're throwing a little like rubber band between our 2 nucleuses or nuclei. Covalent compounds are the same as molecular compounds. So molecular compounds, nonmetals only. And again, we're sharing electrons for these covalent bonds in these molecular compounds. We can represent either of these types of compounds, things that have ionic bonds or things that have molecular bonds or covalent bonds. We can represent them with a chemical formula. We're going to be seeing a lot of chemical formulas in this class, so it's important that we learn how to read a chemical formula, how to write a chemical formula. Chemical formulas tell us the elements that are present and the number of atoms or ions of each of those elements. So the way we put these together is we'll have a subscript, sub meaning lowered, a lowered writing. Following each element symbol, that's the number of atoms of that element. So for example, H2O, the H and the 2 are together. So that lets us know there's 2 hydrogens. And then after that, oxygen. We omit ones just like we did with charge. So with charge we had the superscript, the raised writing. We've got the subscripts in this case. Anytime that we've got a 1, we're just going to leave that off. So it's H2O instead of H2O1. We're just going to assume that no subscript means it's a 1. Sodium chloride is represented as NaCl. So we've got 1 sodium, 1 chlorine. Carbon tetrachloride CCl4, we've got 1 carbon, and we've got 4 chlorines. So that's one way that we can represent a chemical formula, is writing them out. That's usually how we'll see our chemical formulas represented. There are other forms of formulas, though. We also have empirical formulas. Empirical in my brain is basically experimental. So an experimentally determined formula. Empirical formulas give a relative number of atoms of each element in a compound. For example, hydrogen peroxide has HO for its empirical formula. The actual number of each, the true formula for hydrogen peroxide, is H2O2. But we can divide both of these subscripts by 2 to get HO for our empirical formula. So this is the simplest subscript version of our chemical formula. So anytime we can reduce the subscripts, we do so for the empirical formula. So we're going to simplest subscripts. This might give you some flashbacks to algebra, least common multiple sort of vibes. We also have the molecular formula. That's the actual number of atoms. And we can convert between molecular formulas and empirical formulas. Some information is needed to do that. So if we have our molecular formula, this is the number that are actually in each molecule or each piece of the compound. So for C4H4, the greatest common factor is 4. 4 goes into 4. 4 also goes into 8. So we could simplify this. Divide both of those by 4. And you get your empirical formula of CH2. B2H6, 2 goes into 2, 2 also goes into 6. So take 2 divided by 2, take 6 divided by 2, you get BH3 for the empirical formula, the simplest ratio formula. For CCl4, the carbon is already a 1. 1 is the simplest whole number that we can get. So the only common factor is 1, so the empirical formula is the same. Sometimes, not always, but sometimes, the molecular formula is the same as the empirical formula. It just depends on what the subscripts are. We also have various forms of structural formulas or more visual formulas. So in a structural formula, we're going to use lines or we're going to use spheres, something to represent our bonds and our atoms. The type of structural formula that we use the most is going to be, like for H2O, it'll look something like this. So we represent our atoms as their chemical symbol. We'll use a single line for a single bond. One line equals one bond. Similarly, 2 lines equals 2 bonds. 3 lines equals 3 bonds. If I had 4 lines, how many bonds would I have? 4. Yeah. Each line represents 1 bond. We won't see quadruple bonds. They do exist, but not in our class. So we'll have single, double, triple bonds as options. the type of formula that we use depends on what we found or how much we want to communicate. A structural formula gives us the most information because a structural formula can include information like how many bonds there are, the types of bonds. I don't know, I'm so bad at writing right now. Types of bonds, where they are, how things are connected, etc. So it gives you a lot of information. You do need to be able to look at it and pull that information out, right? So we have to know what the lines mean. We have to know what the symbols mean. An empirical formula is going to communicate the least because it just gives us a relative number of each of our elements to each other. It doesn't give us the actual number. Just the relative number of atoms. If we have a molecular formula, right, we can get the empirical the other way. We can't necessarily go from an empirical formula back to a molecular formula. We need extra information to do that. Similarly, we could take a structural formula, turn it into a molecular formula, turn that into an empirical formula. All right, let's get some practice with empirical formulae. So we want empirical formulas for these compounds. We've got molecular formulas given to us. So for our first one, C5H12 pentane, what is our empirical formula for C5H12? It's just C5H12, because carbon has a subscript of 5. The numbers that go into 5, 1, 5. We don't have any other factors. 12 can't be 5 number out. And so we just have to leave it as is, because 5 is prime, and 12 doesn't have 5 as a multiple. What about Hg2Cl2? So both of them have a subscript of 2. We have to divide both of them by 2. So we get HgCl. The ratio for them is 1 to 1. We can also do it for things that have more than one element. So C2H4O2, 2 goes into all of these. So we're going to divide each of the subscripts by 2. And this will be CH2O. A common mistake that I see people make when we're going from molecular formulas to empirical formulas like we're doing here, especially when we've got multiple types of things like C2H4O2, is we'll remember to divide for the C2, we'll forget to divide for one of the other ones. So they might write C2H4O, or sorry, CH4O, or something like that. That's a common mistake that I see people make. So good opportunity to double check your work and just make sure, did we actually divide everything? Questions so far? Related to our structural formulas, I was alluding to molecular models. Molecular models are even better in some ways. They take more time to put together, but they also include a lot of information. So a ball and stick model represents our atoms as balls or spheres and our chemical bonds as sticks. Sometimes they're bendy, and this shows us how to connect them. The balls are typically color-coded to specific elements, the ones that you see up there on the screen. Some of them also play a role for multiple other ones. Just coming back and pulling out some molecular modeling kits. The most common type that you're going to have is the ball and stick version. And so you get little plastic pieces that act as bonds. They're either single bonds or they're multiple bonds, so some of them are bendy. And we can use these bendy ones to form 2 or 3 bonds. And then the balls have little slots in them where you can stick the sticks into, where they stay nice and tight. And then you can connect them to other colors. And if you have the correct number of holes in your different balls that represent your elements, then you get the correct structure for them out as well. We'll be playing with these a little bit later in the semester. There's also more advanced versions, so the ones that have the preset holes, those are the kind of beginner version. There's also versions that have magnets in them that are pretty neat. They cost more money, of course, and they're a little less universally useful, I think. Then the more advanced version, you just have like colored like styrofoam balls and then toothpicks, and you have to decide where to put the toothpicks for the bonds. So these are a much more advanced version, but they let you make more things than with the preset holes. And we'll be playing with those, using those later in the class when we get to Lewis structures. The colors, I would say, not that you need to know them for exams probably, because I print all the exams in black and white, but these 4 are the most common that you'll see: hydrogen, carbon, nitrogen, oxygen. Those are the most common that you'll see in depictions in the slides. So those would be the best ones to know, those colors and all that. And then I was referring to a space filling model. The ones with magnets usually are for doing space filling models. And this actually shows more how they actually exist. There's some overlap between the atoms, or what we consider the atomic shape. So those are kind of cool. Any of these, the structural formula, the ball and stick model, depending on how you draw them, these can be the same amount of information, or the ball and stick model might provide more information. And then here's just some examples of different forms of that, so showing the information that we capture. So for benzene, a carcinogenic compound, the empirical formula is CH, the molecular formula is C6H6. The structural formula, this is how it's actually arranged. And then with the ball and stick model, adding in some color, adding in these double bonds as like the 2 sticks, we get a little bit more of a fun version of the structural formula. But I'm guessing that most of us from the molecular formula wouldn't think that this is the structural formula. This is the actual shape of it. But that's the way that it looks. Others of these kind of have 3 dimensions. They've tried to draw in for things like glucose and ammonia. So depending on how we draw in our structural formulas, we might get that 3-dimensional shape, but more likely, I think we probably won't. All right, big breakdown of elements and compounds. For our pure substances, we can have elements, we can have compounds. Our elements can either be atomic, or they can also be molecular, and we'll talk about those. Our compounds can be either molecular or ionic, and we'll also talk about those, and that's a big part of the nomenclature, the naming convention stuff that we're working towards getting to. Atomic elements exist in nature with single atoms as their basic unit. This is how we've probably mostly been thinking about them. Just one single sphere of that particular element, our single smallest building block. Some examples given. There are also molecular elements that exist, and these are 2 or more elements bonded together. We have 7 diatomic elements listed here, and there's several mnemonic devices for those, to remember those, to memorize those. Those are always going to exist in nature as H2, N2, O2, etc. We also have things like phosphorus and sulfur that exist as polyatomic ions. So when you find phosphorus or sulfur out in nature, it's 4 atoms bonded together, or it's 8 atoms bonded together. Our mnemonic devices for our diatomic elements, I'll talk about on this next slide because there's the visual element to one of them. So one of the mnemonic devices for our diatomic elements is H7. And it's H7 because hydrogen is the H, and then the 7 shape is nitrogen through fluorine, and then down to iodine. So that's one of the ways that we can remember our diatomic elements. The other way, one of the other ways, would be Brinkelhoff, which is just a word that you make out of the symbols. So Brinkelhoff would be another way to remember it. And then there's the longest. Horses need oats for clear brown eyes. And each of those words starts with one of our diatomic element symbols. Horses need oats for Cl, Br, and then eyes, which doesn't start with the letter I, of course, so we swap it out for the letter. And I'm not much of a horse girly myself, so I don't know if this is true, but shout out all the horse girlies. Big year for horse girlies, since it's the year of the horse. Questions about any of those diatomic tools? So you can remember all of them. You can remember one of them. You could also optionally remember none of them and just memorize it some other way. Up to you. I recommend memorizing them because for some reason I love the diatomic elements and testing you on this particular piece of information. I don't know why, it just comes up a lot for some reason. I probably test on it too much. And then there's also polyatomic molecules that are just the things inside of the seven, so phosphorus, sulfur, selenium. And I don't have any fun mnemonic device for those, sorry. Okay, molecular compounds. Molecular compounds are composed of typically two or more covalently bonded nonmetals. Covalent meaning they're sharing the electrons. And our basic unit for a molecular compound is molecules. Molecule is the single unit of molecules, of molecular compound. So when we're talking about one piece of a molecular compound, we're talking about a molecule. For ionic compounds are made up of cations, typically a metal, and anions, usually one or more nonmetals, and they're bonded together with ionic bonds where there's a transfer of electrons. Our basic unit of an ionic compound is the formula unit. The formula unit is the simplest, the smallest, electrically neutral collection of ions. Or another way of thinking of it, the empirical formula of the ion. It should always be an empirical formula. The reason that we call it a formula unit rather than calling it something like a molecule is because when these actually exist, it's alternating positive negative charges. And so if we were to actually count up the number of positive and negative charges, we'd end up with absurdly large subscripts. And so we just simplify it. What's the simplest repeating unit for sodium chloride? It's a ratio of 1 to 1, so we just call it NaCl for our formula unit. It's important that these be electrically neutral for ionic compounds. So the number of positive charges needs to balance out the number of negative charges. And we'll learn more about that soon. So molecular compounds made up of molecules, ionic compounds made up of formula units. We've been talking about things primarily within the realm of just like single atoms, but we also have groups of polyatomic ions. So a lot of ionic compounds, many common ionic compounds contain ions that are groups of covalently bonded atoms with an overall charge. So the polyatomic part, poly meaning many, atomic atoms, so many atoms together, ions because they're charged. Just the whole group of them together carries a charge. So this is many atoms bonded together. They kind of travel as a unit. And the ions part meaning that they have a charge, an overall charge. We're not going to worry right now about where the charge is on the actual ion. We'll just say it has one, and it's somewhere in there. So for example, NaNO3, we've got Na, which is sodium, and sodium is a metal. It forms a positive charge. And the NO3 is a group, and that's the NO3 minus group. And we're going to learn names for a bunch of these. We're going to memorize names for a bunch of these. Do we have questions so far? Trudging through the background, hopefully mostly review if you've taken Chem 20. Okay, we want to classify some substances. Classifying substances is critically important because the way that we classify a substance determines what name system we use. So different types of substances have different name systems. So starting off, fluorine. What kind of thing is fluorine? Is it an element or a compound? It's an element. What kind of element is it? Is it atomic or molecular? It is molecular. Molecular. No, molecular. And that's because fluorine shows up in the hinge of the H7, or it's the 4 in Horses Need Oats for Clear Brown Eyes, or it's the last letter in Brinkelhoff. So it's molecular. That would exist as F2. It's one of our diatomic elements. What about N2O? Is that an element or a compound? It's a compound. What kind of elements does it have in it? It has nitrogen and oxygen, and how do we classify those? Are they metals or are they nonmetals? They're nonmetals. We only have nonmetals, and so that makes it a molecular compound. And then we have silver. What kind of thing is silver? Is it a compound or an element? It is an element. Is it atomic or molecular? It's atomic. We know that it's atomic because it's not part of Horses Need Oats for Clear Brown Eyes or phosphorus, sulfur, or selenium. It's one of our transition metal elements. It's over in that middle block. So it's atomic. Then we've got K2O and Fe2O3. Are those elements or compounds? They're both compounds. What kind of compound is K2O? What sort of things does it have in it? Is it nonmetals only, or is it metal and nonmetal? It is metal and nonmetal. So K, potassium, over on the far left side, it's in our first group, our alkali metals, group 1, group 1A. So this is a metal. And oxygen is a nonmetal. Since we have both, that means it's going to be ionic. And the story is the same for rust, Fe2O3. Fe is iron, which is a metal, and oxygen is still a nonmetal, so that makes it an ionic compound. Questions so far? All right, we're cruising. Ionic compounds show up a lot of different places. Minerals, they're also in some of the foods that we eat. They also, if your water dries out, it leaves behind residue. That residue has a lot of ionic compounds in it. They tend to be very stable. They've got really strong ionic bonds between the positive and negative charges. When we're writing a formula for an ionic compound, we want to write the symbol of the cation with its charge. If we know what the metal is, we should know what the metal is. Then we're going to write the nonmetal, the anion, with its charge, which is going to be a negative charge. And to make the formula for the ionic compound, we need the positive charges to cancel out the negative charges. It has to be electrically neutral. It has to be a neutral formula. So there's a couple of ways we can go about this. One of the ways, some of us will just look at the positive charge, the negative charge, will least common multiple in our heads or whatever the thing is, and we'll be like, okay, we need to multiply the cation by this and the anion by this. We'll put them together and the charges balance out. If you can do that, awesome. The rest of us, we're going to adjust the subscript of the cation and the anion, and the way that we're going to do that is probably with the swap and drop or the crisscross method. So a lot of the time, the majority of the time, we can take the charge and make it the subscript of the other thing, and that will get them to cancel out. Ooh, I zoomed in. We sometimes also need to simplify. Not a lot, but sometimes. So I'll give us an example of one where we don't have to simplify. Let's say that we have calcium. Calcium is going to form a 2+ ion because it's an alkaline earth metal. It's in the second column. If we want nitrogen is going to form a 3- charge. It's going to form a 3- charge because we have to move 3 spots over to get to the nearest noble gas. Neon, it's going to have 10 electrons, 7 protons, 3 extra electrons, gives it a 3- charge. You could also just memorize that that column is a 3-. Some of us in our heads see this and go, okay, well, we need 3 calciums, we need 2 nitrogens, then they'll balance out perfect even Stevens. We can also just crisscross them. So the crisscross, the 2 goes on the nitrogen, the 3 goes on the calcium. So we get calcium 3. We get nitrogen. We've got 2 of those. And then if we check our charges, our charge on our calcium was a 2+ times 3 of them equals 6+. Our nitrogen has a charge of 3-. So we take 3-, we multiply that by the number of that we have, which is 2. So 3- times 2 equals 6-. We've got a total 6-, total 6+. Those are the same but opposite. They'll balance out. We've got a neutral collection of ions and anions. And we can't reduce the subscripts at all. So swap and drop or crisscross works a lot of the time. Sometimes you do have to simplify. Ionic compounds are always going to have positive and negative ions. The first element is usually the metal or cation. It's not always. So if we have the ammonium cation, NH4+, that often gets put at the back, or it can be put on the back end. So metal first, nonmetal after for the chemical formulas. So magnesium oxide, MgO, because magnesium is the metal, oxygen's the nonmetal. It would not be OMG. If you do that, I'm going to say OMG. You got it wrong. Put it in the wrong order. Relatively simple rule for our ionic compounds, the order that we put them in. We've got compounds that we can form between potassium and sulfur. What's the symbol for potassium? K. We love potassium. What charge does potassium form? Plus. We know it forms a plus because it's in the first column. First group forms one positive charge all the time. Our sulfur has the formula S. Sulfur's S. It's in group 6A. Group 6A is always a 2 minus charge. That's 2 minus. So we can swap and drop. The 2 is going to be the only one that actually does anything here. So this would be K2S. And that would be our formula. K2S for our potassium and sulfur compound. Aluminum has the symbol Al. It's in this group. What charge does aluminum form? 3 plus. It's not 13 plus. 13 is 3A. So it's a 3 plus. Nitrogen has the symbol of what? N. What group is it? 5A. 5A is going to be a 3 minus. So it's going to be 7 protons. The nearest noble gas is neon, which has 10 electrons. It's going to have that number of electrons. 7 protons, 10 electrons, 3 extra electrons. Electrons are negatively charged. 3 minus charge, so N 3 minus. If we look at it, we've got 3 plus, we've got 3 minus. We can just combine those to get ALN. If you swap and drop these, because some of us just want to do the same thing every single time, and that's fine. If we swap and drop, this is going to give us Al3, N3. Is that the same thing as ALN? Is it exactly identical in every single way to ALN? No, it's not, because we've got the 3 that's there, right? So we have to see that we've got 3s. We can reduce that. We divide each of those by 3. And then it becomes ALN. So Al3, N3 is incorrect. ALN is correct. So just make sure that you're thinking about, if you're swap and drop every single time, make sure you're thinking about, can I simplify those numbers? Usually the answer is no, sometimes the answer is yes, and when the answer is yes, you have to simplify. Okay, so that's some of the coming up with formula stuff. Now, we're finally at the start of nomenclature. So ionic compounds are what we're going to name first, because arguably they're the easiest, or at least easy-ish. This is our introduction to systematic naming. Some compounds do have common names, just because that's what we've called them forever. Like water is a common name. Salt is a common name. Sugar is a common name. They all mean a specific thing. They mean a specific chemical. They could also mean groups of chemicals like sugars, but we also need to know the systematic names, and that's arguably more important than having the common name. So the first part of naming something, identifying the compound. Identifying the compound is the first step in naming compounds. We've got at least 3 different systems for naming that we are going to cover. There's more than three systems of naming. The first part is figuring out which of the 3 systems do we put it through. So the first step in naming an ionic compound is identifying that it's an ionic compound. They are usually composed of a metal and nonmetal. We could also have a different cation instead of a metal. Cations and anions. That's a little bit more general, a little bit more broad, so it includes that ammonium that was mentioned briefly earlier, H4+. And this is some examples of what those would look like. We've got sodium, that's a metal. We've got aluminum, that's a metal. We've got calcium, that's a metal. We've got magnesium, that's a metal. So we see a metal, chances are good that we are working with an ionic compound. So for naming ionic compounds, there's 2 systems. two general splits in our tree, or one general split, I guess it would be. The first type, this is the easier type, the charge is invariant. Variant meaning it could change, in meaning it can't. So it can't change. So that means that it's always the same charge. So our metal, our cation, always the same charge. That's one group. Then we've also got metals with a charge that can differ, multiple charge options for the metal. We're going to talk about the first one first, and then we'll talk about the second one after that. Second. Okay, so metals that form one cation are these ones. So we've got our group 1A, our group 2A. We also have group 3A in here. And then we've got some weird ones. We've got scandium, we've got zinc, we've got silver. Those are our transition metal elements. So metals that form one cation are going to be main group metals, generally. Not all of them get included in this. And scandium, zinc, and silver. When we are naming these, the metal comes first. We name the metal first. The names of the ions are the same as the element names. So calcium 2+ is the calcium ion. It's important that you put ion after it so that we know that we're talking about the 2+ form of it, not the Ca. The ion part meaning that it's that ion form. So that part, we're just going to name the metal what its name is. When we put it into the compound, we don't include the ion part. There's also metals that form more than one cation. So here's some of the metals that form more than one cation and some of their compounds, or some of their ion forms. These aren't all of their forms. Good news, bad news. Good news, we're not going to learn or memorize all the names. But as some of you might read from that, that implies that we are going to memorize some of the names. So we get to, since we're in Chem 1, we're going to memorize more of the names. We're going to have more of those under our belt. So there's one system, the new system, stock notation. Thank you, Alfred Stock. The stock notation system is the one that shows up here under name. So for chromium, when it's a 2+ ion, we put a 2 in parentheses after it. So charge in parentheses after the name. We love stock notation. Even if you don't love the notation, trust me, you love it, because the other option is the older notation. In the older notation, we've got endings of OUS or IC. So you take the base name, chrome in the case of chromium, and you add OUS or IC, and that refers to one of two different options. So chromium 2 is the chromous ion. So Cr2+. The stock notation, chromium 2 ion. Older notation, chromous ion. The higher charged one, chromium 3, takes the ic ending. So OUS is the lower charge. IC is the higher charge. I'd like to point out that lower charge and higher charge, the OUS, the IC endings, do not include all of the possible ions. So chromium, for example, can also form chromium 6. We don't have an older notation version of that ion name. I'd also like to point out that OUS and IC don't always mean 2 and 3 charge. So chromium 2 is chromous, chromium 3 is chromic. Iron 2 is ferrous. So the base name, we're now going back to the original, the FERR, that's where we get our symbol from. It's also 2 and 3. Cobalt is 2 and 3. Copper 1 is the OUS, and copper 2 is the IC. So you have to memorize the numbers, and then the higher charge one is the IC ending, the lower charge one is the OUS ending. For tin, it's 2 and 4. For lead, it's also 2 and 4. The most practical application of these older names is that sometimes you will see these older names in like a nursing or health context, like ferrous or ferric ion. And so that's part of the reason why it's important we talk about it. Lots of people who are taking chemistry are going into health pathways, and so it's important that we, at the very least, be able to recognize them when we're done, but hopefully also know what ion they're referring to be able to separate the two. This is part of our chemical nomenclature literacy, being able to read the chemical names. Another trick, Mrs. K's trick, my mother's tricks, but I also like this one. It's a way of remembering that zinc and silver are 2+ and 1+. There is a little staircase here. So aluminum is at the top of the staircase. That's the third step. It's the top step. Just down one from the third step would be what step? The second step. So zinc is a 2+. And then if you go down one more step, you're on the first step. Silver. Silver is +1. So aluminum is a 3+. Zinc is a 2+. Silver is a 1+. And scandium is also in there on the other side of the transition metals. There should be, at the very least in your lab manual, an ions you need to have memorized sheet. I think it's in our lab manual. It might also be up as a separate thing. Those are ones that you do have to have memorized. Not for our first exam, but second exam and onward, they're all fair game. So some of those could show up. We also have anions. We've got monoatomic anions. Monoatomic, the mono means one atom ions. One atom anions. We change the ending to IDE. So for example, if we have fluorine, chlorine, bromine, any of these non-metal elements, you take off the ene, the the ogen, the orus, and you swap in IDE. So F- is the fluoride ion. And if you're just talking about F-, you can just talk about it as fluoride, because the ion part is implied because we changed the ending to IDE. It's a little bit less important that we have the ion part for the name. These all have predictable charges, so we're kind of just mentioning we changed the ending to IDE. So when we're naming binary ionic compounds, which we will be naming binary ionic compounds, binary meaning we've got two options, two things. The binary compounds have two different elements in them. And the naming is actually quite simple once you get to the names, once you've got the names of the cation and the anion, you just combine them together. So for our cation, our metal, it's just the name of the metal. And then you take the base name of the anion, you change the ending to "ide", because it's a negatively charged ion, and you plop it in there. You just put them next to each other, boom, that's your name. So for example, KCl K is potassium. Cl is chlorine. It's in a compound, so it's negatively charged. It's ionic. So we make it chlor, and then we have to change the ending to IDE. So the full name, potassium. Name of our metal, base name of our nonmetal, change the ending to "ide." For CaO, same process. Ca is calcium. The O is oxygen. The base for oxygen is ox. We change the ending to IDE, calcium oxide. Questions? Okay, some examples. Ag3N. What is Ag? Ag is silver. So we write silver. Is Ag always the same charge? It is. It's always a 1 plus. And then what is N? N is nitrogen. The base is nitr. And then we change the ogen to ide. So it's silver nitride. Where did the 3 go?
They evened out.
We don't need the 3.
Yeah.
We don't need to include anything about the 3 because we know that silver is always a +1, right? So let's look at if we were going the opposite direction. Silver, okay, we memorized that it's silver plus. Nitride, that's referring to nitrogen. Nitrogen, we would also memorize, is a 3 minus. If we crisscross it, Ag3N. So it works forward, it works backwards. We don't need to specify the 3 because we know what the charges of both of the parts are. That's why we don't need to specify for the 3. Okay, rubidium sulfide. Rubidium is Rb. Rb, and it's a 1 plus because it's all the way in the far left column. So Rb plus. Sulfide, the sulf part, is referring to sulfur, S. It's in 6A. It's 2 spots over from our noble gases, S2 minus. Do our crisscross, our swap and drop, and we get Rb2S. When we're using binary compounds that have multiple charges, multiple charge options, we can either use the OUS or IC ending name, chromous, chromic, ferrous, ferric, or we can use the stock notation where we have the charge in parentheses. This is the new notation, newer notation, stock notation. So for example, CrBr3. CrBr3, we need to do a little bit of sleuth work. Cr is chromium. What charge does chromium have? Chromium is one of our transition metals, so we are not sure. Chromium, it's got multiple options, so we're going to have parentheses. Then we're going to look at our anion. What charge does our anion, or what is our anion? Sorry. Bromine. So the ending will be bromide. What charge does bromine have when it's bromide, when it's the anion? It's going to be Br minus. And we've got how many of them? 3. So 3 times 1 minus, that's a total charge of 3 minus. Right, so our total negative charge is 3 minus. We've got 1 chromium that has to balance out a 3 minus charge. So what charge does it need to have? So chromium gets a 3 plus. It's going to be chromium 3 bromide. Or chromic bromide. They're the same, just one's newer. You need to be able to recognize both. Questions? All right. Some more. I'll give you some time to work on these, work with people in your group or around you if you need to, if you'd like to. All right, we've got some compounds. We've got the formulas for one, we've got the name for the other, and we want to get to the other thing. So starting with FeS, Fe is our symbol for iron. Iron. Iron is one of our transition metals. It's not scandium, zinc, or silver, and so it could have multiple charge options. So we want to have a little parentheses behind it, because we don't know what the charge is. And putting the parentheses in there hopefully will remind us we have to figure out what the charge is. The other thing, S is sulfur. Sulfur, we start with sulf, we change the ending to IDE, so sulfide. Sulfur, when it forms an ion, is a 2 negative charge. We've got one of them, so we've got an overall negative charge, 2 negative charge. We also have 1 iron. The iron needs to balance it out. See if we can write it. So we're starting by looking at our sulfur. Our sulfur is a 2 negative charge. We've got one of them, so it's an overall of 2 negative. The iron, on the other side, we also have only one of them, and we need to figure out what the charge is. It's going to be some x plus. In this case, x times 1, x plus times 1 equals x plus. So x plus is going to be equal to 2 minus, or the same charge, opposite. So it's going to be 2 plus. We probably, hopefully, need to do the, write out the formulas to figure it out, but we can do that still anyway. So it's going to be iron 2 sulfide. Or, I believe this is also ferrous sulfide. If there's 2 options, you need to name them. I also meant to do a review of Roman numerals, because I recognize that not all of us have our Roman numerals memorized. So here's up through 10. Got I, we can't believe it, IV, V, and so on and so forth. Okay, we've got ruthenium, IV, 4, oxide. We want the formula. So ruthenium, Ru, the IV meaning that it's 4 plus. Oxide, the base is oxygen. Oxygen forms a 2 minus charge. Then we can crisscross. We'll get Ru 2 O4. Can we simplify? We can simplify, and so we need to simplify. So divide both of those, each of those by 2, and it turns into Ru O2. So that's ionic compounds, binary ionic compounds with monoatomic anions. We can also have polyatomic anions. So these are basically the same, except that we're going to use the name of the polyatomic ion whenever it shows up. We do have to memorize names and formulas for polyatomic ions and anions. So for example, NaNO2, the Na is the cation, Na plus sodium. The polyatomic anion, NO2 minus, is nitrite. So we have sodium, nitrite. There are many polyatomic ions. One large group of them is oxyanions, which I believe I've got slides for, yeah, right after this. So some of the common ones that aren't oxyanions, things like acetate, the hydrogen carbonate. The hydrogen just means we've got a hydrogen in front of carbonate, also called bicarbonate. That's a common name. Hydroxide, dichromate, ammonium, cyanide, and peroxide. Those would all be polyatomic ions that are not oxyanions. I believe the rest are oxyanions. Your green sheet, the green handout, has many of these on them. So if the side that doesn't say solubility table at the top is oxyanions. We're going to talk about those in just a sec. We've also got the naming rules for you to reference. There's also some extra rules, so adding the hydrogen in front as a prefix, like we saw with, like I was showing us here with this hydrogen carbonate. Hydrogen meaning we've added one hydrogen in front. You can also have dihydrogen, like for phosphate, 2 hydrogens in front of phosphate. And each one we reduce the negative charge by 1. And then there's some other common polyatomic ions at the bottom. Okay, into our slippery web of oxyanions. So oxyanions, similar to our metals that can have different charges, we've got a little bit of a system here, but there's also some memorization involved. So most of our polyatomic ions that we'll see are oxyanions. The oxy part referring to oxygen, and then there's some other thing in there, and they're negatively charged. We usually have a series of oxyanions. So like we had chromic, chromous, we usually have different endings, sometimes different beginnings, for our oxyanions. When we have two ions in a series, if it's just 2, the more oxygen atoms has the ATE ending. The one with fewer has the ITE ending. The one with 1 fewer has the ITE ending. So on the green sheet, the oxyanions table at the top, those boxes are laid out in the order that the non-oxygen thing shows up on the periodic table. The boxes are arranged like that. And it's the ATE ending. So borate, carbonate, nitrate, etc. The ATE ones are the ones to memorize. You also need to know, right, the number of oxygens and the charge. The number of oxygens and the charge can change for our ATE ending. Question?
How would you know which one has more oxygen atoms and which one's fewer? Like in the elements of compounds. How would you distinguish which one has more or less?
ATE always has more, ITE always has one fewer. There's not like a rule for remembering the number of oxygens. You have to have that memorized. So nitrate, you'd memorize NO3 minus, nitrate. Nitrite, okay, ITE is going to be one less, so NO2 minus.
So then if it would be like NO4 minus, that'd be an 8 as well, right?
Yes, it would also be an 8, but there's another thing that we can do with that. If we have more than 2 ions, sometimes we have more than 2 ions, then the prefixes, hypo, meaning less than, like hypoallergenic, things that are supposed to cause less allergies or be good for people with allergies. And then we also have the per prefix, meaning more than, like if somebody's hyperactive, they have more energy, an excess of energy. So we've got per, hypo for prefixes, and we can add these on in addition to our ATE and our ITE endings. So just looking at 2 possible series here, our reference is chlorate. Chlorate has the 8 ending, it's ClO3 minus. We can go from the 8 ending to the ite ending, subtract 1 oxygen. Right, so instead of ClO3 minus, it's ClO2 minus. Now it's chlorite. The ending has changed. If we take 1 more off from the ITE ending, now we add the hypo in front. So this adds to the ITE ending. It means take 1 more off. So if you've got the ite ending, take 1 off. If you've got the hypo prefix, take another 1 off. They're additive. For our 8 ending, you can also go up. You can add 1 oxygen. So ClO4 minus, you get the per prefix on there. So per just means add 1 more to whatever your 8 ending was. It'll always be per and 8 that go together. It'll always be hypo and ite that go together. Never hypo and 8. You're never going to have hypochlorate. That's not a thing. You're never going to have perchlorite. That's also not a thing. Another thing that I'd like to point out, this is kind of nice. Notice that the charge is the same. For every entry in a series, these are both happen to be 1 minus. For all of these, it's a 1 minus charge. So charge doesn't change. SO4 2 minus is sulfate, just to give us an example with more than 1 charge. If we take this down to SO3 minus, SO3 2 minus, that's the wrong colors. SO3, that's the one that changed, 2 minus. This is sulfite. So the charge is always going to be the same. The way that we change the oxygens with the name is always going to be the same. The number of oxygens for the 8 ending is not always going to be the same. It's frequently different. I think it's always 3 or 4 though. Questions? the more that we use these, the better we'll get at them. I've been using them a lot, and so they are just like instantaneous, which is cool. But I recognize that for you, this is like you haven't been dealing with these for years, every day, thinking about them late at night. And so you are not going to be instantaneous at them. That's why we have a nomenclature worksheet. That's why we've got practice. That's why I recommend making flashcards to help you memorize them. It takes work. You put the time in. So more tricks. Memorize the ATE ending. And then the hyper prefix adds 1 oxygen. Relative to the ATE. I is the light version, like Bud Light is low calorie Bud. Hypo prefix means less than, and it still has the ITE ending. The textbook, I think, shows it in the opposite direction, which is crazy work. A little bit of practice. We want to name this compound SnClO3 2. So if we've got multiple, we've got 2 ClO3 groups, we have to put it in parentheses and put the 2 outside to show that we've got 2 of that whole group. It gives us more information than distributing the 2. And the way that we read it off, SnClO3, and then a little break, and then 2. The little pause lets you know that we're talking about we got 2 of the whole group. Or you just, have the name on command further down the road. What is Sn? Sn is tin. Where's tin live? Tin is in the 4A. We don't know what the charge is. Tin something. So we'll have to look at our anion, our ClO3. So we, for now, right, look to our green sheet, find the chlorine oxyanion. We find it, chlorate, ClO3 minus. Chlorate, ClO3 minus. That's the group that we have, right? It's ClO3. That's what we have. So we write chlorate. We know that it's chlorate because it's the same number of oxygens. If it was a different number of oxygens, we have to do a little modification to our name. So we get the chlorate ending. And now we have to figure out what's the charge on our tin. So tin, we've just got one of them, so it's relatively easy, right? Our chlorate. We've got ClO3 minus. We've got 2 of them. So 2 times 1 minus, we've got a total 2 negative. If we've just got 1 tin and it needs to balance out a 2 negative, it's got to have a 2 positive. To balance out the 2 negative. So it's going to be tin, 2 chlorate, or what's our other form? Stannous chlorate. Question?
Do we have to memorize all the Latin names?
You have to memorize some of the Latin names because the OUS or the IC, the old version names, use those as the base. So yeah, the ones that show up in the nomenclature section, there's things you have to memorize. All those metals that show up there you have to have memorized. Or you're expected to have memorized. You can always choose to not memorize them and just take the point hit. But yeah, you would memorize stannous for tin 2. All right, then we've got cobalt 2, phosphate. Cobalt 2, what's the symbol for cobalt? CO, what's the charge? 2 plus. Phosphate, the phos base tells us phosphorus, so we find phosphate on our green sheet. PO4 3 minus. That would also be the one that you'd memorize. PO4 3 minus is phosphate. We swap and drop. C little o 3. PO4 2. What's wrong with this? We need parentheses around the PO4. If you don't have the parentheses, it might look like PO42, which is crazy. So parentheses are required. This could also be, is it cobaltous phosphate? Probably. Another reason that it's good to know these OUS and IC names, not necessarily to have them memorized. I expect that we'll forget them after this class. It's good to know that they exist because sometimes, like, chemical companies or just manufacturers of products might choose to use cobaltous or cobaltic instead of cobalt 2, cobalt 3 on their product information. Or if you go look up older research papers and you see cobaltous, cobaltic, we want you to have in your brain that's referring to there's a specific charge of the cobalt, or oh, there's a specific charge of the iron. We want you to have that in your brains. There are also, in addition to just the massive amount of fun that we've been having with ionic compounds, we can also hydrate them. If I say that I'm hydrated, what does that mean? I'm full of water. I got lots of water in me. I've been drinking water, right? Water inside of me. Hydrates, similarly, ionic compounds, hydrates are types of compounds that have water molecules with them. And we write them with this dot operator, or middle dot. This dot means associated with. I don't know if that's exactly what it means, but that's how we should interpret it. So the formula for Epsom salts, like you might use if you're taking a bath, MgSO4 dot 7H2O. The systematic name for this would be magnesium sulfate. Mg is the magnesium. It's only got one charge option. SO4 is sulfate. And then we would call it heptahydrate. The hepta prefix is for 7. Hydrate meaning waters, so 7 waters. So this is a hydrate. This is a picture of cobalt 2 chloride hexahydrate. There's also an anhydrous version. The an prefix meaning no. Anhydrous meaning, meaning no, water. So without water, or the hydrate with water. Hydrates generally are ionic compounds with water in them. We're not going to really get into details about, I think, where the water molecules are, what they're doing. We just need to know they are there. And usually hydrates have a different color from their anhydrous version. We should see some examples of that later in the class. These are our prefixes. So more fun prefixes to memorize. Many of these, I think, will come a little bit more naturally to us. mono, di, tri. I think those ones I would guess that most of us have down. Tetra is 4. Penta, 5, like the pentagon, 5 sides. Hepta has an X in it. 6 also has an X in it. Hepta is the weird one. One of the weird ones. Octa, like the octagon or an octopus, 8. Nona, our Italian grandmother, another weird one for 9. Nona for 9. And then deca, like decade, 10 years. So naming some hydrates. CaSO4 middle dot 1/2 H2O. This is calcium sulfate what did I do? Hydrate. BaCl2, Ba is barium. It always forms the same charge. Cl is chlor. It's got the "ide" ending, so barium chloride. How many waters do we have? 6, so hexa, hydrate. We can also work backwards. For example, copper 2 sulfate pentahydrate. CuSO4 dot 5H2O. Copper is a 2+, sulfate's a 2-. They balance out, so that's why it's 1:1. The penta prefix meaning 5, and the H2O for hydrate. I'm rushing because I'm running out of battery, mentally and iPadically. Okay, molecular compounds, very brief coverage of molecular compounds. These cannot be readily determined based on their constituent elements. So with the ionic compounds, we know what the charges are, so we can do a little bit of algebra and figure it out. For molecular compounds, it's not the same way. We can combine nitrogen and oxygen in a bunch of different ways like we see here. These are each things that exist. You can go out and find them in the world. You can make them in a lab. If we try to use the same system, these would all be some form of nitrogen oxide, which doesn't work because there's different options there. And so for our molecular compounds, remember our molecular compounds are made up of nonmetals. We use numerical prefixes. The more metal-like element is first. There is a system, you can look up and find the order that they go in. I'm not too worried about you memorizing the order, but usually the thing that's further to the left shows up first. The thing with the smallest group number. And then we're going to be using those same prefixes that we saw for hydrates. We are just going to use binary molecular compounds for now. We'll do a little bit beyond binary molecular compounds perhaps. They have the form prefix, name of the first element, prefix, base name of the second element, change the ending to IDE. So relatively straightforward. One little caveat. One atom of the first element, mono, is omitted. So NO2, N is nitrogen. We've got one of them, so our inclination might be mono nitrogen. How many oxygens do we have? We've got 2, so we put the di prefix. The base for oxygen is ox, and we change the ending to IDE. We do have to remove that mono in front, though. We omit that. It's just one of those chemists like to save time and space, even if it's insubstantial. It's a little more substantial, so we just omit it. So if there's no prefix on the first one, we assume that it's 1. H2O and NH3, we're going to generally use their common names, water and ammonia. Okay, some compounds that we can name. Name the compound N2O5. What's the first thing that we have? We have nitrogen. How many nitrogens do we have? Two. So we're using the prefix for two, di. So dinitrogen. What's our second thing? Oxygen. So we're going to use the base, ox. How many do we have? 5. What's our prefix for 5? Penta. Oftentimes, if you've got your prefix ending in a vowel and your word starting with a vowel, we get rid of one of them. So pent, ox, and then we change the ending to IDE. It might also sometimes be spelled out, pentaoxide, but it's always pronounced pentoxide. Big emphasis on the maybe about having the A in there. So usually we cut one off. If you don't cut one off, guess what? Every chemist still knows what you mean. So it's not a big deal. If we're trying to write a formula for phosphorus tribromide, what's our first thing? Phosphorus, which has the symbol P. How many P's do we have? 1. What subscript do we write? Trick question, no subscript. Okay, what's our second thing? Brome, the base for bromine, bromine. Br, how many do we have? 3, because of the tri prefix. PBr3. Isn't that nice and simple? Love it. Yeah, we'll stop there for today. We'll pick up with more next time.